Okay, so let's start and finish. So if you remember, last time we finally quantized those Rebai algebras in the sense that we found deformation of UG. And there is one little thing which is not really necessary, but let's have a look at what happens with those Poissonly groups, whether we can make this formal quantization, formal in the sense in formal neighborhood of identity, whether we can extend it to the group. So quantization of Poisson Poisson groups, and we're going just to use the same method. Basically, also everything is going to be the same. So if you remember, the method was of where to get Hopf algebras was that we started with some braided monoidal categories D and C. So these are braided monoidal categories. There was some functor which was braided comonoidal, and there was also a co-commutative coalgebra. And there was still some compatibility condition between F and Q, this kind of admissibility. And so from that, there was a Hopf algebra which was just F of QQ. And it was supposed to be some sort of analog of how to get the group from its nerve or something like that. So analog of G is equal to G times G modulo G. And today, that's exactly what's going to happen. Even Q is going to be G. Everything is just going to be exactly as is written there. Just the category needs to be defined a little. So which categories? So for that C, I'm going to take just manifolds. But we need to extend morphisms. Some extended. Okay, so let me do it this way. So C0 will be this manifolds, or C infinity, and morphisms. Well, morphisms, whatever I say. Something from M1 to M2. That will be, by definition, will be maps, linear, going from C infinity M2 to C infinity M1. And composition is defined as composition in the opposite sense. In principle, like, these are way too many morphisms. We're not really going to use all of these. But we're not going to use just, say, pullbacks by smooth maps. There are going to be some differential operators. So just imagine that things are going to be like smooth maps and possibly some differential operators composed with smooth maps or something like that. But if you wish, you can demand that these linear maps are continuous or something. It will not hurt, because anything that we will see will be just differential operator anyway. So we're here. Now this guy is a symmetric monoidal category. So what is M1 tensor M2 is simply M1 times M2. Or if you wish, that's if you pass to those algebras of functions, that the tensor product of two algebras of functions is defined as the algebra of functions on the products. That means that we're taking this completed tensor product, if you wish. But yeah, this is the definition of how it's a symmetric monoidal category. And okay, C that's going to be C0 H bar. That means that we're going to work. Morphisms are going to be also formal power series in H bar on top of this. Okay, so that's where we're going to find our Hopf algebra in this stuff. Now, who is D? This is something very similar. So let me first start with D0 again. So objects are again manifolds, but with some action of something. So just, okay, maybe I need some notation that G is our Poisson group. And then we need the Drinfeld double of its Lie algebra. So D is the that means that G star is the Manin triple. So there we are, and now we need manifolds with what? With an action of D. So D is supposed to act there, but we also suppose that such that when you look at the action of G, who is part of this, so that G gives, such that the action of G in D gives a free and proper action of G. So, okay, so that's it. So we don't say require that the action of D integrates to action of the group, but what we do require that at least that Lie subalgebra G acts there so nicely that it's actually free and proper action of G. And okay, given what I actually defined, let's suppose that G is connected so that this makes sense. One can make sense of it also for non-connected groups, but I would need to say something. Okay, so there we are. And so who is going to be D without 0? So D without 0 is D0 and then H bar and phi. Do you see how it is that I can use this? Because D acts here. So we have action of our, or one can say that this category can be seen as a kind of version of the category of UD modules. Just D acts on functions. How is it? On C infinity M, say for every M using D0. And so from this we'll get action T who sits in S to D. D acts on C infinity M1 times M2 for any M1, M2. Just do. The first component acts here, the second component acts there, as we have this D action, and this is the morphism. So, and this is T M1, M2, going from M1 times M2 to itself. So this is all. So that's how we make this to an infinitesimally braided monoidal category. So from that we see that D0 is a infinitesimally braided monoidal category. That's it. And now we can just make run all that machinery. Now that we know those two categories. So what do I need? I need a co-commutative coalgebra Q, right? So there should be some Q in D, which as a category or is basically the same as D0. So who is going to be Q? Q, by definition, that's going to be simply G. Now, how is it a coalgebra? So we should have a coalgebra means that we should have a morphism going from G to G times G. That means that it should be a map going from C infinity G times G to C infinity of G. But I will actually take just simply the diagonal embedding. So it will just the diagonal, and if you wish, is diagonal. The pullback by restriction to the diagonal. So this is somehow the actual map, even though in principle there are many more morphisms than simply geometrical maps, but here I will take this geometrical map. That's perfectly okay. It's a coalgebra. And so it is certainly a co-commutative coalgebra in D0. When we don't quantize and when there is no associator, then everything is fine. This is co-commutative thing. Commutative coalgebra in D0. And the thing is that this G is again infinitesimally commutative, or co-commutative, sorry. You remember there was this definition of infinitesimally co-commutative or commutative. There was this thing that you apply the coproduct and then you place here T. So what you call like from G to G times G and then to G times G, you put T, G, G. This is our coproduct. It's probably easier to read it the other way. So that you take C infinity of G times G, then apply this differential operator T to C infinity of G times G, and then just restrict to the diagonal. And we did this calculation. We did this calculation saying that this is 0, so this is supposed to be 0. And
T, is it anything or?
This T is the thing. Okay, is the thing coming from the action of D, and now I see that. Yeah, I forgot to tell you something. Well, I told you, I told you the thing say long ago, but I should remind you. In what sense G is an object here? So it should be a manifold on which D acts. And so how is it that D acts there? The idea is that G. Okay, we have. G sits inside of of D, and then when we look at what happens with this map when we go to D mod G star, then this is actually a local diffeomorphism. It's a local diffeomorphism, and therefore D acts on G, which implies D acts on G, and that's sort of complicated action, or for that one needs to understand who is D, who is G star, etc., to understand exactly what is this action. But when we just look at action of G on G in this sense, what happens? We're supposed to simply multiply on the left by a thing from G, or we multiply somebody who is in G anyway on the left by somebody from G. So G acts on G by left multiplication. So that's how G is an object in our category. Yeah, so the action of D for that one is to understand all those details, but for the action of G there is nothing to understand. It's simply the action by left multiplication. Okay. And then we made this calculation. This is 0. So why is it? The idea is because the stabilizers of the D action on G are coisotropic, or in fact Lagrangian. And do you see why? Say, what is this when you have this G thing? And then if I start with 1, just imagine that G is locally identified with this thing. So what is the stabilizer of 1? G star, yeah, right, that's. So at least somebody is not sleeping, right? So we divide here by G star. So the stabilizer is G star, right? So here, stabilizer is equal to G star. If you take some other point, and the stabilizer is going to be conjugate to G star. So G, and this is going to be something like G star, G inverse. Sorry, for stabilizer I should probably, okay, it's action of Lie algebra, so now it's going to be totally unreadable. This is what happens. So this one is Lagrangian by whatever definition of Manning triple, and this is just conjugate to that, and the inner product or the pairing is invariant, so therefore it's Lagrangian everywhere. Okay, cool. So it's a nice object, this thing. G is seen as a coalgebra, or if you wish, the algebra of functions on G is seen as an algebra in the end, that it's infinitesimally co-commutative. So this was the most difficult part. So what is F? I can fit F here. So F is going from D to C. And who is that? This F of M is equal to M mod G. I think that, yeah, we suppose that the action is free and proper, so this is a good thing. And how is it comonoidal? It's sort of obvious how it's comonoidal. So let me write it somewhere. So for that we should have these kind of morphisms. And who are they? Well, this is M1 times M2 mod G, M1 mod G times M2 mod G. There is this one obvious map which goes from here to there when we mod out even more, and that's the one that we're using. Nothing ever changed. So again, this F is infinitesimally braided comonoidal functor when seen as going from D0 to C0. So this implies that the same F is a braided monoidal functor once we go from D to C. And that's it. Now what do? We have F and Q. So what do we still need to check? Probably that F is say, G admissible. But there is frankly nothing to check besides recalling what is G admissible. But G admissible meant that it kills one G. F is there exactly to kill one G. It's modding out by G. If you multiply something by G, then F will remove that G. So whatever the definition was, it fits the definition. The definition was actually motivated precisely by this example, so there's nothing to check here, really. And so this implies that F of G times G, which is simply G times G of G, is a Hopf algebra in this category C. And this is nothing, okay, that we can identify with. That we can identify with G, and this is what we wanted. One should then say, still check that okay, say we have there is a coproduct. So there is some kind of quantized coproduct going from G to G times G, or in other words, it goes from C infinity G times G to C infinity of G. So this is an associative product. So this gives you associative product on C infinity of G. When you just restrict to functions who are products of a function of one from one G and on the other G, you get that thing. What one should check probably is that it's actually a star product. That it's not just simply an associative product, but it's of the form that it's a star product. If you remember, star product means that it's a deformation of the ordinary product, and that all those deforming terms are by differential operators. But I can leave it as sort of exercise. It's simply by construction, it's like that. Okay, so that's roughly the end of this story of quantization of Poisson groups.
How do we know we didn't get the same G back?
Sorry?
How do we know we don't get the same structure back?
Yeah, right. So I'm now skipping maybe too much, but see, we verified for last time we verified when we were deforming UG, and we verified that that the coproduct is deformed, that the coproduct is something like delta H bar, that it's delta 0 and plus this H bar divided by 2 times the Lie cobracket and plus whatever. What's happening here, it's really the same definition. Everything is the same, just this is a local calculation around around the origin, like in form of power series, if you wish. So when we replace the group with the enveloping algebra, and so the thing that one needs to verify, but it's exactly the same calculation as here, is that when you look at this coproduct, or meaning this associative product, and you compute the corresponding Poisson bracket, that you actually restore the Poisson bracket which is on the Poissonly group. We are certain that we're getting a Poissonly, well, you see, certainly from here, we'll get a Poisson bracket on G, right? So any deformation of the commutative product gives you in first order Poisson bracket. Since this stuff is actually Hopf algebra, then this Poisson bracket is not just a Poisson bracket, it must be a Poissonly bracket, so it must make G to a Poissonly group. But then one needs to verify, so to which Poissonly group, and you're perfectly right, it might happen that this Poisson bracket is just 0. That would be sort of a shame, right? So with all these silly constructions, it just get 0. But one can compute this Poisson bracket either explicitly everywhere, it's doable, or one can simply compute its linearization at the origin, that's even easier. And you would see that the linearization of this Poisson bracket at the origin is exactly the delta. The calculation is the same as we did here. So this Poisson bracket on G, and from there, linearization at origin is small delta. Okay, so I didn't want to spend too many details on that because we did spend too much time already on this quantization of UG, which is probably more important thing than this quantization of Poissonly groups. But at least it's good to know that one can do it. Okay. And now for something completely different. Yeah, but anyway, don't take this too seriously. This is the last lecture. Just enjoy your cherries.
I am.
Okay. So somewhat surprisingly now, at the very last moment, I will start talking about something completely different, as I said. So, but let me just say a couple of words and see where it ends. So it's going to be Kontsevich or universal Vasiliev not invariant. So it's a thing that has something to do with this class, but not too much. So that's a nice way how to end it. Okay, so what is it about? Since I at some point, which came way too early, stopped following this quantum topology class, I have no idea what you did even in first term, and absolutely no idea what you did in second term. But you probably were talking about some knot invariants at some point, no? That at least they say you take some quantum group, possibly just SL2. It's perfectly fine if you just take SL2, and then you draw some knot, and which I'm not capable of course. What is the? Okay, let me try to draw this thing. Okay, like this. Yeah, I didn't turn properly, sorry. you know, if I spent an hour on training that, I can do it without erasing. Okay, so you take some node. This is the only node that exists apparently. And then you would probably take some representation of your quantum group, and then the node must be oriented. Okay, there is just some orientation, and it should also probably be like framed. Something that one should imagine it's actually a band, which is in the space. Then you imagine that reading it this way, that each time you see arrow pointing up, then you see this representation V of your quantum group there. You see the dual of that thing. Now here would apply the R matrix for exchanges, and now there is this creation of like going from 1 to V star tensor V, and here this annihilation and going from V star tensor V to 1, etc. So you just read it as a morphism going from 1 to 1, which is a number, and that's your number, which depends on if it's like UQ, SL2, or whatever was the thing. The number is a function of this Q, also known as the Jones polynomial. And then, okay, that's probably when for V you take this fundamental representation as two-dimensional thing. And okay, that's roughly it. Now we're going to look at something which is sort of more perturbative, so maybe less interesting, because when we see this Q as exponential of h bar or something like that, and then we expand everything in h bar, we get some formal power series, which is then way too complicated, and we're just going to look at this formal power series, but in some wonderful, nice way produced for us by associators. So it will be some associators, and if you take an associator, it produces this not invariant, but which in the end doesn't depend on that associator, it turns out. So we can actually scratch off the associator. So what is it? I don't know, maybe to make more sense of it, like you can start with arbitrary, nice braided monoidal category. Nice means that it has those duals that that these kind of things make sense and those kind of things make sense, thing which is called a ribbon category. And then every time you pick an object, every time you see a knot, it will produce you a morphism from the unit object to itself, which is going to be that invariant. And we saw some nice braided monoidal categories coming from a Dreamfell associator, and that's roughly what we're going to use. But then we just circumvent those braided monoidal categories because they are not really needed. One can just draw everything as a picture, and it's nicer. So there's something called chord diagrams. So did you meet these? Okay, so you already know what. I mean, did you meet in this class of quantum topology or in some other class or somewhere? No. But you just met them during your life. But, yeah, so let's meet them again, all friends. So there is a version which is just for a circle. So imagine that you have a circle, some sort of skeleton of our chord diagram, and now we would draw some chords on the circle. The circle should be oriented. The chords are not oriented, and So chord diagrams of just 4 more linear combinations. Linear combinations of these pictures, but modulo relation that we know very well. I will write it the way we know it, and then I will draw what it means. So which is that T A B in bracket with T, how should I write it? Maybe T A C plus T B C is equal to 0. So what does it mean? Just imagine I can draw this circle any way I wish. It doesn't matter. It's just a picture. Now imagine that this is a part of the circle. And it goes on, then it returns, goes on, whatever it does. That's not supposed to sit in the plane. It's just an abstract circle, abstractly connected by chords. So I simply take 3 pieces of the circle, put them side by side like this. I call those pieces A, B, C. It might be, I don't know, like this might be A, this might be B, and this might be C, who knows, something like this. And suppose that now in this little part I can draw what this means. So TAB it will go like this, and now here is TAC. So I need to draw those points where it's attached, which is just going around, and plus the same thing. And now BC. So this is equal to the same as when we first multiply by that and only then by that. 1, 2, 3 plus 1, 2, 3. And so the thing that you see here is TAB times TAC and plus TAB times TBC is equal to, well, the other thing when it's in the opposite order. So those are these relations for any, whenever you take 3 small arcs on the circle, whenever you see something like this plus that is equal to this plus that. So say, just for notes, these kind of chord diagrams are perfectly okay when there is a single circle, but more generally, that skeleton, the circle may be replaced by we replace circle by say, any one-dimensional, maybe compact oriented manifold, which is just a wonderful way of saying that it's a collection of several circles and possibly several intervals. I admit here also with boundary. So it means that you might have, say, 2 circles and also things like that would be also chord diagrams. Now one can probably ask what is that space, right? So where you get this. The definition is not so difficult. Well, there are these pictures modulo those relations, but can one understand this space? And one probably can, but I cannot. So the only thing I can tell you that the space of those chord diagrams is graded by the number of chords. Certainly, these relations, they don't change the number of chords, so this makes sense. And each graded piece is finite dimensional because there are only finitely many configurations one can imagine with n chords. So at least it's always finite amount of work to understand that space for every n. Okay, and so what is that concept which is not invariant? There is not. So it's usually denoted Z, and what it does, you take a knot, it goes from knots to chord diagrams, or more generally, if you have several things linked, so if you go from links, chord diagrams, say on a circle, from links it would go to chord diagrams, but on as many circles as there are in the link. So it's a not invariant whose values are these strange pictures. Then if you want to get some numbers, then you actually need to define some way how to get from these to numbers. But this invariant is universal in some class, but I will probably explain what that means, etc. after a break. So let's restart. So I sort of defined those chord diagrams without any motivation. The relation was the relation that we already saw, but why to define it like that? That was somewhat unclear. So I'll give you some reason or some way how to get those chord diagrams, even though I will not prove that it's actually true. So one way how to look at it, that you can start with knots, the set of all isomorphism classes of knots. Let's take the vector space spanned by these things, what we'll say with rational coefficients. Generated by that. And now this thing is naturally, or one can even put here Z if you wish, that doesn't really change anything. So this thing is naturally filtered, also has a decreasing filtration. And the idea behind this is somehow how you might be able to simplify a knot, or how to, if you have something very knotted, a way how to unknot it is to, whenever you see some crossing, you can try to replace it, you can try to cross it, to pass to the other thing. And the idea is that whenever you see such a difference, so imagine that it's a node which continues, goes on, and the same node, we only replace a little part in this node. We get a linear combination of two nodes in this way, and this is supposed to like go in the filtration by one. Each time you see a difference of two crossings. So that's how somebody being of filtration as n is defined, that you can actually find a knot, or maybe form a linear combination of knots drawn in the plane, and then you do this operation to it n times. So you apply this difference operator n times. That means that you're getting somebody in this filtration n. And it's not true. What? So, what?
I didn't understand, sorry.
Ah, okay. No, but that's okay then.
Yeah,
No, I mean, okay, let me draw some knot. Let's say knot. Now one needs to like choose those things, right? So somehow. Yeah, possibly it's going to be unknot, I don't know. No. I have no idea what this is. Possibly it's unknot.
There is still one.
Yes, there is one intersection.
Okay, then let's do something with it. Here it goes over, so let it go under. Let's say knot. Well, there are many ways how to draw this knot. Possibly, as was suggested, this might be another way how to draw the same knot. I don't know. But so what you can do now to this knot, you choose one of those crossings, like this one, and make out of this the difference of two knots. So it's going to be this formal linear combination where you keep the original knot and minus the same thing, but with exchanged. Well, what was over is now going to be under. And now you apply this operation n times.
Can
Like-
you use just change the same thing at some point?
Yeah, I don't. Let's not do this. Yeah. Okay. Let's always choose something different. Okay, so let's do it like n times. So you get the combination of two, with 2 power n things, right? And you would say that this linear combination, some of them are going with pluses, some of them are with minuses. So this thing is in this Fn vector subspace of this guy. And so the reason why to do it at all, why to look at this thing at all, is that you might try to simplify a knot or to turn into an unknot by exchanging those overcrossing with undercrossing, like that. And then when you actually want to compute some knot invariant, then it's good to know what happens if you do this operation, and if it's somehow reasonably enough, so you finally get it to the state where it's actually an unknot, and you look at apply all those rules and compute your knot invariant, something like that. And there's some sort of abstract nonsense around that let's do this filtered vector space, and now one can ask what is the associated graded vector space. So there is associated graded, and what is that? Those are chord diagrams. And how that happens, roughly, or not so roughly. So the thing is that, well, what I drew there, so this minus that is the same. No, it's not the same. So this, well, in this associated graded, so it's not really equal, but it goes to to when, well, there are those two things. Now they are abstract, they are no longer in R3, you just understand it's abstract one-dimensional thingy. So let me avoid them, but for that crossing, you would draw this chord. That's the relation between those things. And this is, of course, a statement that one needs to prove. Well, it's not entirely obvious that this is true. Okay, but I will not prove it. Maybe one useful thing is that this queue of nodes, or just nodes form a monoid. So one can multiply nodes, or there is this connected sum, which is in per product. So you have one node and another node. Both of them are supposed to be oriented. It's like this. Should go like that. So the operation that you would do is connect them. One is to verify that this is actually a well-defined operation, but I don't know if all of you already saw these kind of things, then I can just skip it or something. But so how does one verify that it's a well-defined operation? The idea is you need to shrink one of those nodes into something very small, and then you can walk with it around the other node and put it in any place. That's why it's clear that it doesn't matter where you actually stick those two things. So that's why it's well-defined. And it's certainly commutative because, well, there is no difference between who is first and who is second, so it's a commutative. And those chord diagrams form a commutative algebra. So chord diagrams were on a circle. Form a commutative algebra. And how is that? Again, by connected sum. So what do? Imagine you have two chord diagrams. And here you have another chord diagram. So how do you compute it? Well, you take what those things should be oriented. So you make connected sum of those circles, and that's the product in our algebra. One needs to prove that it's well defined. If what I told you there were true, then it seems that this should be a corollary of that thing, and it is. But one can just verify it directly. And I can leave it as sort of exercise. When you really need to use, you see, without imposing those relations, this is not true. Chord diagrams were defined as chord diagrams modulo some relations. Without imposing those relations, it's not true. This operation depends on where you apply it. So you choose two different points, two different short arcs on your circles, you merge it, but the result will depend on where you do it. But the fact is that you can somehow, again, slip this thing through anything exactly the same way as here you could shrink it and slip it through anything. And that's a corollary of those relations. You can.
And it's not even necessary to imagine that this intervals, this chords are in fact just the double points of projection of the knot. Because then this four-term relation has a simple interpretation, and you understand why it's corollary from that.
Yeah. Okay. So basically, you're saying that it's, somebody competent should be talking about this stuff. Okay, so anyway, so it's a whichever way you define it is this thing, and now. So what is this concept which is nonsense? So the idea, or how to get it, I will simply define it, tell you how to compute it. So how Z, so that's going from knots to chord diagrams, and what we need an associator. So here I wrote, if I write here Q, then possibly we should take associator with rational coefficients, but whichever. It might be, say, with coefficient in C, it doesn't matter. X, Y. Say of weight. So that was this thing which I called mu. Equal to 1 to normalize things. Let's do it this way. And now, when you see a knot, when I draw a knot, you just interpret it as a diagram, as a morphism, so to say, and you just read it off and draw everything you need. So basically, so what you would do? So each time, say if you have a portion of a knot, or possibly of a link, which is a braid, is a parenthesized. So what would you do this? What do I mean by that? I mean, you draw your knot like this, draw all those crossings, which I don't care about actually draw. And now we are trying to read this knot in this direction. And sometimes there are some creations or possibly annihilation things, so these things that don't look like a braid, but maybe there is a portion, like, I don't know, between here, this blue looks very white, right? And here. So there it looks like a braid. It doesn't look very parenthesized, in the sense that these points, they are just somehow randomly distributed. But in that case, let's just parenthesize it somehow. Or, maybe let's bring those things close together. So let's choose some parenthesization. So whenever you see such a thing, then do a braid on, I don't know, k strands. Now, using that associator, we can assign to it element of tk, right? We assign to it element You still remember how it was done? So it was this thing, like when you see this thing, like re-bracketing, then you assign to it the associator, and when you see a thing like this, then you assign to it this R matrix, or which is like exponential of 1/2, and if I write here AB of T AB. Right, so this is ABC, and should be T AB, TBC. cool. So for any such portion of the node, we have a thing like that, and now we interpret it as a chord diagram. So this element of tk can be seen as what is called the horizontal diagram on k strands. So how do you see, what does it mean? You just draw those k strands, and now each time, say, here is, I don't know, this one, whatever, A, B, C, D, E, and now if you see a thing like this, what is this? This is TBC times TCD. And so anything from here, so which is contained in, well, completed enveloping algebra of this dk is a linear combination of things like that, and you just draw it as a chord diagram. So now in place of writing symbols, we will just draw those chords. That's it. That's very easy. But then we need to decide what to do when there are some new things possibly appearing. So some new things. So this is all. This we already saw. First new thing is that our node is actually oriented. So we'll so the idea is that, well, things this comes really from when you imagine that everything is actually given by a Lie algebra, and that you have a representation put on those strands, and when going down means that you have the dual representation, and then you need to change the sign. So that's where it comes from, this ideology. So the idea is that if, say, A, B, C, D, so if you see somewhere like TAB, you should place here this bar, this chord between A and B, but one of those strands has the opposite orientation. In that case, you're supposed to put it there with sign minus. So in this case, you're supposed to take this, but with sign minus. So it means that, well, if it's like this or like that, then the sign is plus. Or here the sign is reversed twice, if you wish. So that's why the sign is plus. But if it's this way or that way, throw it like this, then it's going to be minus. So that's the rule for putting there those chords. That the TAB is not necessarily the same thing as the chord. It's going to be chord up to a sign. The problem is that, roughly speaking, that B thing is not really B, but it's kind of dual B. is going down, some b with star, and t of, or if you wish, it's something like a rule that t ab star is equal to minus t ab, because here we're acting on the dual representation. Okay. So this is one minor problem. And there is another minor problem that our knot is not a braid, usually. So we need to do something when two things actually meet, when there is either cap or cup. We need to do something in that case. So the second new thing is how to interpret, or how to deal with these and those. No, one natural idea was just let's ignore them. When this happens or that happens, okay, we don't put there any chords. But this is not a good idea. It doesn't work. Why it doesn't work? Or what should actually work? The problem is that if you have something like this, so that, and okay, I can do it this way. This should be the same as that. And if you look at how this is composed, you see, we're going, if you read it from bottom to top, then at first there is this single strand, then there is this birth of those two, of particle and then anti-particle or something. So that's what's happening here. But then what's happening here? You see, it's associator. There is this guy moving here. That guy, when they're born, then they're close to each other. They're parenthesized so that everybody else is more far away. But then this guy is being moved here. So what we see here is actually the inverse of associator because I'm going this way. So, okay, anyway. And then finally, there is annihilation of these two things. And the result should be this, which is just nothing, right? Here, there is no chord produced whatsoever. So what should happen? So the thing that should happen is that we need to assign something to those cups and caps so that when multiplied with the associator, you get 1. So the idea is that one need to assign to this some alpha and that some beta. These are chord diagrams. And such that, so how should I put it? Such that when you take the products, how is it? Phi. Okay. Alpha times beta times phi inverse on a single strand is equal to 1. Is it I'm not sure, it's probably not sure whether it's understandable what's happening. You see, The problem is that I told you that chord diagrams form a cumulative algebra when they are on a circle. Now this is not on a circle, so let me secretly close it. Just imagine that, just to put it on a circle. I'm going to totally ignore any rules how to actually compute with those chord diagrams for this part. I'm only using this part. Let me also close this circle secretly to a circle. And now what you see here, I might say that this is connected to here. It is connected sum of this with that, and this with that. So we need to put some. Okay, here is some horrible chord diagram corresponding to this phi. So it's something like this. Linear combination of things like that. So TAB and TBC. Linear combination of things like this. But I need to put something here and there to kill it and to get one. But to put it, I can put it this way. That I have here some alpha and here some beta. So putting that alpha here just means that I open it and do that thing, open it here, do that thing. And now the statement is that the product of alpha, beta, and phi inverse, it's a cumulative algebra. It doesn't matter in which order I multiply it. That this thing should be equal to 1. Now this phi inverse put on a single strand, that's what you see here. So when you take this phi, but then you close. So phi inverse on a single strand, that's when you take phi as a chord diagram, and then you close it you close this skeleton of the chord diagram according to that rule. So that's what I mean by this. Or in other words, that alpha times beta is equal to phi on a single strand. Now one needs to choose. Now the best choice turns out to be when we take the square root of the thing. So the usual choice. Then it works, because then certainly alpha times beta is equal to that. And now, well, the theorem just says, so that theorem is that this rule, or this method, how should I formulate it? Let me call it rule, which goes from links to diagrams, that is actually well defined. It's links, okay, I should say probably from framed. And so it gives us, it produces not invariance. So what you want to prove? You see, this method of how we starting from a node or from a link, how we produce the chord diagram, it depending on how we place the knot into the plane. It depends on the projection and how we parenthesize things, etc. Now the statement is that if you take the same knot or link and put it differently, you get the same stuff. But why is this? I will not go into detail of the proof because I didn't prepare anything. But basically, there are the only things that you would be doing that. You can describe those links or nodes in terms, say, of Reidemeister moves or something like that. And or the big part of all of those moves is already covered by simply in braids. We already know that it produces a braid invariance. We know that that's a method how from a braid we produce an element of Tn or Tk, for sure. And for the rest, there is only, say, there is only this rule, which I erased here, that this thing is equal to that. That's a thing which is not in Reidemeister moves, but that's somehow when you want to get from braids to knots, then we need to impose this additional thing. And there is also there's Reidemeister 2 and Reidemeister 3, which are in the definition of braids. There is also Reidemeister 1, which is that thing. And this is not true in this case. We would need to artificially impose it, so this is not true. But that simply goes into this being framed, so we just need to count the number of twists when we go around the knot or link. Okay, so that's it. Now, as it turns out, this invariant is actually independent of associator for some very nice reasons, but let me not go into those very nice reasons. Let's just say finish this class early and so that everybody's happy.
What is universality?
Yeah, I didn't tell you for that I should tell you what a finite type invariant means. Finite type invariant means that, well, when there was this filtration defined, it means that it's something which vanishes for anybody who is far enough in that filtration. So meaning that when you exchange n times overcrossing with undercrossing, then it will stop being sensitive to such a thing. That's a finite time invariant. And now this Quantization invariant, well, how is that? I told you that there were those knots, Q of knots, and there are those chord diagrams. And that this guy is the associated graded to this filtered guy. And that Quantization is invariant. What it does, it goes like this, and it's actually compatible with the with the filtration in the sense that then we can go from gr of this is equal to this CD thingy. The associated grade is equal to that. And from here, we can go to CD with this gr of Z, but that gr of Z is the identity. So somehow that Z doesn't lose anything. Or what it really means that any finite type invariant is obtained from this Z by what factors through this Z. And any finite type invariant would be something which, by definition, is something that goes from CD to, it must go from CD somewhere, wherever, and it always is of this type. So that's this universality.
And this is proven, or?
Yeah, not here, of course, but I didn't prove anything today. Sorry.
But this is like known fact.
Yeah, it's a known fact. It's not terribly difficult. Yes, I just wanted to tell you something completely different, and then probably didn't fail at telling you something completely different, but it failed at any explanation. So, okay, I just finished like this.